Okay, before we get started, I just want to remind you that there is a stability chart of how carbocations are most stable, and there's reasons behind this, and really and truly, these two happen to do with resonance. That's very important when we look at a lot of the reactions involving benzene. So, the most stable carbocation would be the benzylic, then the allylic, tertiary, secondary, primary, right? So you're not going to have an sp2 carbon involved in with a double bond, that's an sp2, right, with a positive charge on it. Either of these, they're just not going to happen, okay? Just want to make sure everybody remembers that. So when we start dealing with benzylic position reactions, let's look at the oxidation reactions. You can do this with Na2CR2O7. The cool thing about this particular reaction is that if there is any benzylic hydrogen there, so in other words, if there's not a carbon that's attached to four things, it will kind of like cut off whatever you have here and put down benzoic acid. So I kind of tell people this is sort of like, you know, those fancy scissors that you use and can leave little patterns as you cut through things? Well, basically that's what the oxidation is of the benzylic position. And you can do that with Na2CR2O7 or you can do it with KMNO4. Either one should work there. So if there's two of them, yep, going to replace both of those. You can barely even stop it. But if there is a carbon that has four bonds, there's no benzylic hydrogen there, nothing's going to happen. So no reaction will happen there. And just as a reminder, bromination, you can use Br2 and UV light, NBS and heat, any combination of those two. That's pretty much the same thing because NBS makes Br2 in situ, right? So what that's going to do is it's going to allow the bromine to go to the benzylic position, similarly as it did with the allylic position that you should have seen before. Okay, why is this benzylic position so incredibly awesome? It's because of resonance. So I just want to get you all used to what resonance sort of looks like here. And so if we're thinking about benzylic positions, electrons can move here. That moves the positive charge there. Remember, positive charges don't move. They are a result of electrons moving. Okay? So these electrons will go there, then positive charge will be there. These electrons go there, positive charge will be there. And this is a different resonance structure than this guy. So a lot of times what we actually think of these as is, what do they look like when you average all these resonance structures together? And that's what we refer to as the resonance hybrid. And that's why you see me draw a lot of circles in the middle, because in truth what that means is the electrons are delocalized for purposes of the aromaticity that we talked about last time, right? But what that would mean is the positive charge is actually spread throughout four different atoms. So here, 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 and here. And that's why it's so stable and why you can get that positive charge more easily in this type of guy than you can anywhere else, because the allylic you can at least spread it between two carbons, right? Here and here, but these are kind of stuck where they are. Okay. So that leads us to thinking about what happens when other types of reactions happen at that benzylic position. That's why they're so easy to occur, is because you can go through SN1 reactions really easy at the benzylic position. So here, these reactions will work all day long. You don't have to do much, just putting in water, and that should work without a problem. It also means that E1 can occur, and you can end up getting a double bond right there, or E2 can occur, and you can get it right there. Now be careful. Just because I draw this circle on the inside, remember that there's a double bond here. I've seen people before try to draw a double bond right this way. That would be 5 bonds to carbon. Will not work. Okay. Now, we've talked about how stable benzene is. It's one of the few things that will not react with palladium or platinum with H2. That shows you just how stable this is. But if you start increasing the temperature to 100 atmospheres, that's pretty high. And nickel and H2 in a high temperature, it will eventually do this. So, if you want to just reduce styrene, you can just do palladium and platinum on H2, and that will work. It's not going to touch that benzylic position. So just to let you know. And finally, let's talk about the Birch reduction today. The Birch reduction is pretty cool. I'm not going to go over the mechanism per se, but this benzene with Na, methanol, and NH3, ammonia, right, is going to give you this guy. Now, what that's actually doing is it's giving you an isolated diene. So you're reducing one of those bonds, but not all of them. So something to note here is that when you have an electron donating substituent, which I realize we haven't totally talked about yet, that's something that's going to come in the next few lessons. This guy will actually be connected to that double bond. But if you have an electron withdrawing substituent, then it will specifically not be in that double bond. So just something to think about here for right now is that R groups, so in other words, alkyl groups, push electrons in. That's the reason why it's here. A C double O bond will pull electrons out, and that's the reason why it's not involved in that double bond. Okay, thank you.